practically, most of the semester is dedicated to this idea of diagonalizability. Why? Because being diagonalizable allows us to do so many things. We can solve system of differential equations using diagonalization. You can also do principal component analysis using diagonalization, although it's a slightly different diagonalization. So this question of being able to diagonalize a matrix is quite important. We already know one criteria for it being diagonalizable, which is that if you have a matrix that has all distinct eigenvalues, then it's diagonalizable. That's one criteria. And here's another. If a matrix commutes with its adjoint, this being the transpose and complex conjugate, if it commutes with that, then it's diagonalizable. Now this doesn't mean that any diagonalizable matrix commutes with its adjoint. And one example was we saw that 1102 is not normal, right? It doesn't satisfy this, but this is diagonalizable because if you take the determinant of this, then you end up with AD minus BC, so it's just 1 minus lambda times 2 minus lambda, so that its eigenvalues are 1 and 2. But 1 and 2 are distinct eigenvalues, so I know that this is diagonalizable. Okay. So let's, yeah.
So the A times A star is just like another test that we can use.
Yeah.
So when we do that, is that when we use the normal matrices? Is that typically for like Hermatian, where it's like there's an imaginary component to it?
A lot of times, this you check this in a complex vector space. In the real case, I know that symmetric matrix is normal. Skew symmetric, which is like if you have a real matrix that's negative of its transpose, that's also normal. Just see that it satisfies this easily. But I'm not so sure if there should be some other cases. I'm not so sure though. All right, so but I want to explain this. I can't prove this, but I just want to explain why this is true. Now, to explain this, I also have to talk about the Jordan canonical form or Jordan normal form. Right? So you had a small work for last 2 weeks ago, right? You saw how Jordan normal forms work. So let's review Jordan normal form and see how it works. So suppose you had like A times V1 as lambda 1 V1 and A times V2 as lambda 2 times V2. So imagine that A is a 4 by 4 matrix and you could only find 2 eigenvalues. Right? And diagonalizability is same thing as there exists a basis vectors of eigenvectors. That's what it means. It's vice versa. Same condition. But let's say A is not diagonalizable, so that let's say lambda 2 is like the repeated eigenvalues, which only has one eigenvector, and the other two. I mean, you need 4 vectors to span a 4-dimensional vector space, but it turns out that you can't have any more eigenvectors other than these 2. So in that case, what you do is you have to find the generalized eigenvectors, which is like if you have this applied to V3, it's equal to V2. and A minus lambda 2I of V4 is equal to V3. So you have a chain of eigenvectors. So V1 is like the one with lambda 1. So for lambda 1, you have just V1. But for lambda 2, you have a chain of generalized eigenvectors. V2, but then there's a chain. So these are not eigenvectors. Not eigenvectors. But instead, they satisfy something like this. Now, in such a case, if you multiply A by the the matrix P formed by taking all these generalized eigenvectors as column vectors, then A times V1 will be simply lambda 1 V1. A times V2 will be lambda 2 times V2. But now let's see what A times V3 is. Well, what does this say? This says that A times V3 is equal to V2 plus lambda 2 times V3. Isn't that right? Because if you multiply this with this, it's just lambda 2 times V3. Identity doesn't do anything to the vector, right? So you have that, and then if you move this to the other side, this is what you get. And over here, if you do the same argument, what do you get? A times V4 is same as V3 plus lambda 2 V V4. So that's what we have. We have V2 plus lambda 2 V3, and then V3 plus lambda 3, lambda 2 V4. Now the trick is to rewrite this as a product of two matrices. Again, make this first one as the same thing. The matrix that we usually call P. This is a P matrix. And then think about what goes here. Well, lambda 1, 0, 0, 0. This times this will make the first part become multiplied by lambda 1, right? So if you have lambda 1, 0, 0, 0 multiplied to this, you're going to be multiplying 0 to these, but lambda 1 will be multiplied to every one in here, so you are going to get lambda 1 v1, right? Actually, this is the important part. You may not been paying attention to the previous ones, but this is the important part of the discussion. You have to know that lambda 1, 0, 0, 0 multiplied to this matrix, when you do across down, this will always pick up the elements in V1, so that V1 will be multiplied by lambda 1. Is that good? That part should be obvious if you do the matrix multiplication in your head. Okay? So if that's obvious to you, what should be the second column? 0, lambda 2, 0, 0. So that lambda 2 gets multiplied only to V2. Okay, if you understood that, then now here's the real challenge. I need the third column. If you can figure out the third column, you know Jordan normal for it. What's the third column? 0. No. I need V2 plus V2 lambda. V2 plus lambda 2 V3. 1. V2 has to be there, multiplied by 1. Okay? And then I need lambda 2 here. And then 0. If you multiply this with this, now then all of these will be picked up, multiplied by 1. And all of these will be picked up, multiplied by lambda 2. Okay, what goes here then? 0, 0, 1, lambda 2. Okay? So, if you have a 4 by 4 matrix of this form, this kind of structure of the generalized eigenvectors, then we know that if I call this P, and then you multiply this P inverse to this other side, what you see is that the Jordan normal form for A would be P inverse AP equal to lambda 1, lambda 2, lambda 2, lambda 2, with 1, 1, like that. Okay? And this one here is called Jordan normal form. Some books call it Jordan canonical form, but that causes some problems with the general vocabulary of how the word canonical is used in math, so we try to change that vocabulary. We now try to call it Jordan normal form. But in many textbooks, you'll still see JCF used for this. So having this means that the matrix A is not diagonalizable. Okay? Having those, for each of these generalized eigenvectors, you're going to see the presence of 1 right above the diagonal. And that's called the Jordan normal form because that's the closest you can get to a diagonal matrix. Okay? And, I mean, if you have the Jordan normal form, although it's kind of complicated, it is possible to calculate the matrix exponential to solve system of equations, so they do get used. It's just that we're looking for diagonalizability. This just means it's not diagonalizable. Okay. So going back, so we did a review of what Jordan canonical form, Jordan normal form is. And we actually know another thing about normal. We know that if AV is equal to lambda V, then A star V is equal to lambda bar V. Right? In other words, if you have an eigenvector of A, then being normal means its complex conjugate is the eigenvalue for the same eigenvector for when you consider the adjoint of A. So how are those two related? So what I'm trying to say is basically that if a matrix is normal, if it commutes, then no such generalized eigenvectors would exist. Now, why is that? Well, let's try to do that. So this is not a proof. I'm just trying to give you an explanation why it would go wrong. So suppose, let's say, so kind of proof. Not really a proof, yeah, kind of proof. Suppose you had a generalized eigenvector. So let's say V1 is the eigenvector for A with lambda as the eigenvalue. And you couldn't find sufficiently many eigenvectors so that V2 is a generalized eigenvector. Yeah. I just want to show that such a case wouldn't exist. Okay. So the way we do this is we take, so suppose you have such a thing. Then what you do is you take A minus lambda I V2 oh, okay. All right. So, okay, suppose this is true and AV1 is lambda V. Well, so this is saying that V1 is the eigenvector with eigenvalue lambda. Then we can say that V1 norm squared is same as this with V1. Right? Because this is V1 and that's V1. V1 inner product with itself is norm squared. Right? Now we move this to the other side, right? And then get V2 of A star minus lambda bar I V1. Because when you move an operator to the other side, you have to take the adjoint, right? But adjoint of I is itself, because I is a real matrix, complex conjugate doesn't do anything, and I is diagonal, so transpose doesn't do anything. Lambda is a complex number, so only complex conjugate will introduce this. And then when you apply the complex conjugate and then transpose, we'll have this. But wait, what is this? We just said that this is, if this is true and it's normal, then this is true, right? Yeah. So if I multiply these two, it's going to be lambda bar V1 minus lambda bar V1, which is 0, right? Any vector with the inner product 0 is 0. Well, what does that mean? That means V1 is 0. Right? Then V1 cannot be an eigenvector because 0 vector is not considered as an eigenvector. In fact, V2 will become the eigenvector because this is 0. Right? So what we arrived at is a contradiction. If we say that there was a generalized eigenvector with a non-zero eigenvector V1, then you get that non-zero eigenvector's norm has to be 0, which is a contradiction. So no such generalized eigenvectors can appear. All right? So that means when you try to do the Jordan canonical form, there are no generalized eigenvectors, so you only have genuine eigenvectors. The eigenvectors will form the basis, and now you see that it will be diagonalizable. Okay? So that's how you know that it's diagonalizable.